obvious force law in electrodynamics. Next slide. Our force law is based on a notion that is missing from all previous work on force laws. If you take a magnet or two wires running a current through them and put iron filings around them, you will see that they make a pattern. We call that pattern the electromagnetic fields. In the approach that we have taken, we say that a charge is not limited in extent by the size of the charge, but that it has infinite extent because the fields extend the charge to infinity. That means that if I have two charges, let's say that at the center of this pattern we had two charges, and these are the field lines between them, that the force on the two charges, no matter what their distance, is determined by the interaction of the fields, the extended fields of the particle. So it's not action at a distance. It's always local contact forces. And philosophers have always said for thousands of years there were no other kinds of force but a contact force. Quantum mechanics, special relativity, general relativity, all and covariant electrodynamics based on Maxwell's equations all assume action at a distance forces which are illogical. And there's all kinds of experiments you can do, like you can put a sheet of lead in between two poles of a magnet, and nothing can go through there, no exchange particles or anything, and there's still a force. And it's impossible. There's logical contradiction, but everybody ignores that today. But there's problems with the previous theories. Next slide. Now, what is the origin of gravity? If we only have electrodynamic force, what produces gravity? Well, I wasn't the originator of the idea of what produces gravity. These other people like Cassis and Dragon came up with the idea first, and maybe they weren't original, but that's as far back as I could trace it. The notion is that if you have a neutral dipole that consists of a positive and a negative charge that are in a bound state, such as, for instance, an electron in an atom being bound to the protons in the nucleus, and this electron vibrates back and forth toward the nucleus and then back out, that could interact with another neutral dipole undergoing the same interaction, and there would be some net force between them. Well, now, if you just look at the electrostatic forces, they both have a plus and minus charge, and if they're fairly far apart, then the static forces all cancel. So you wouldn't have any net force. It'd be zero. However, in the universal force law that I have derived, it turns out that some of the higher order terms in V over C do make a negative attractive contribution all the time if you have a force between two neutral dipoles. So that's what we took advantage of, that idea. So here you can see, I can write down in the next slide the force law, and this is our universal force law, and I've expanded it. I took away all the acceleration terms. And by the way, if you take the acceleration terms away, this force law that we're using for this derivation is exactly identical to the covariant electrodynamic force law of Maxwell's equations combined with special relativity theory. So this derivation holds for both that version of electrodynamics as well as the one that I'm showing you, that we're promoting. And so what I did is I expanded the force law in terms of powers of V over C, or beta, and only went to beta to the fourth because I was able to see from the properties of materials that if you look at the velocity of free electrons in a material, such as a wire, and you ask what is the strength of V over C squared, for instance, it turns out it's 10 to the minus 20th power. And so V over C to the fourth power would be 10 to the minus 40th. And difference between the strength of the Coulomb force and the strength of gravity. So we had the idea that gravity was due to a V over c to the fourth power term in the expanded universal force law. So that's why we calculated this, and then we went ahead and in the next slide we actually calculated what you would get, and the top line is what we obtained for the actual force. And if we define mass in terms of these quantities, N2, Z2, A2, A is the amplitude of vibration, omega is the frequency for this neutral dipole that's vibrating. If we calculate the if we can set mass as mass 1 is everything that involves a 1 subscript, and mass 2 is everything that involves a 2 subscript, and then what turns out G is whatever's left over, and you can't determine mass 1 or 2 or G to be the actual value that we measure, because this method only gets the value to a constant. In other words, you could multiply and divide the numerator and denominator of this expression by any constant you want and break it up into any method that you want. So we don't have a unique value for m, but we know that m is proportional to everything related, m1 for instance, proportional to everything that has a 1 subscript there. Well, you can see I put in some ideas of how you might break things up, but you won't be able to get a value of G out. Some people have actually put in constants there, basic constants, and gotten a value of G to be close to what we measure it. We could do that, but we don't think that's significant, because what's going to happen from our work is it's going to turn out that mass is not a fundamental quantity, so we didn't think we should spend that much work on it. The next slide What do you show on your next slide?
Decay of the force of gravity causes?
Yes, okay, good. Now, let's go back to that previous slide again, if we could. In this motion, we have a vibration. Now, according to the laws of electrodynamics, whenever you have a vibration where there's any acceleration of the charge, and of course, when you have an oscillation back and forth, there's acceleration. It stops at one end of the motion, then accelerates, and then stops, and then accelerates back up. So you've got acceleration in both directions going on. Whenever there's acceleration, there must be radiation, and if there's radiation, there's decay in energy. So what this force law is telling us is that the force of gravity must be decaying over time. Now that is different from any previous theory of gravity. For instance, Newton's universal law of gravitation, mass is a fundamental quantity. It does not change. In Einstein's theory of special relativity, mass increases with velocity, but it has a minimum value when it's at rest. And also in his general theory of relativity, mass is a fundamental quantity. So this differs from those theories in that mass is not a fundamental quantity because it's decaying, and anything that's decaying is not a fundamental. Okay, let's go to the next slide now. The decay of the force of gravity is something that's unique to this approach, and it will be the deciding factor on whether or not this approach to gravity is valid. It will be the clear defining factor to show the superiority of this approach if it's true. So what are some of the things that come about if you have decay of the force of gravity? If we think about, for instance, creation, and the thing that was created in Genesis 1:3 was a star, then as gravity decays rapidly, the force holding this star together decreases very quickly, and the star expands. And it expands very rapidly, and the molten gases that were in the star initially on the edge can cool to the point that they form water and earth and other materials. Then the decay of gravity will not stop just because the edges have cooled, but it will continue throughout the lifetime of the star, and we'll see that there can be the crustal material that was formed originally will continue to expand, and as it expands, it will crack. It has a certain amount of elasticity, but only so much, and it will crack. And so if there were water under it, the water would be released and could cause a flood. And then more expansion would allow the water that flooded the Earth at one point to no longer be enough water to flood all of the land, because now the Earth is bigger. And then more expansion would cause the Earth to not only have the waters as flood recede into a few places on the Earth, such as oceans, but it would also leave stretch marks on the Earth. And we will see that. I'll show the evidence for that later on. And then finally, if the Earth continues to expand, the surface of the Earth will get so thin that the hot interior, which is a star, will finally melt it again. And so we see this dynamic. So this is the general picture that's caused by the decay of gravity. But there's many other things that this force of gravity predicts. So we're going to go now in through a lot of that data and see what evidence we find for this new theory of gravity. Next slide, please. If all of the atoms of the universe are decaying, gravitationally wise, this oscillation of electrons with respect to protons in the nucleus, then all the atoms of the universe are giving off radiation. And that radiation should be the largest, most dominant radiation of all the universe. It comes from every bit of matter in the universe. And most of the matter in the universe is hydrogen. So what we did is we calculated what that radiation pattern would look like. We got, and if it came from ring electrons, which are vibrating with respect to the nucleus, and we assume the nucleus is heavier than the electron, and so most of the vibration is just in the case of the electron, we found that we were able to predict a black body classical radiation from ring electrons that fit the cosmic background radiation if we simultaneously asked how strong the force of gravity would be, we got the value of G. So in other words, by asking that the force of gravity decay to what we observe today, and we asked what would the radiation be from that strength of gravity, we found that it matches the current observed cosmic background radiation. And not only that, the next slide shows that this radiation is lumpy, corresponding to the distribution of matter in the known universe. This is all COBE satellite data for both the cosmic background radiation and the distribution of the radiation in the universe. So the lumpiness of the radiation and the actual value of the cosmic background radiation comes from the decay of gravity. Now, no other theory of gravity has anything to do with this radiation. That's a separate effect due to something else. Whereas in this approach to gravity, we predict this must exist, and it is there. The next slide, please. This version of gravity that we derived there were two terms that we obtained for gravity. The first term is very similar to Newton's universal law of gravitation, which has a 1 over r squared dependence, but the second term was a non-radial term, and this term causes what we would call quantization effects in gravity. And so if we look at our solar system, this second term says that the radii of the orbits should be quantized, the thickness of the orbits on the surface of a toroidal ring should be quantized, and that the spin of the planets on their axes and the moons going about the planets on their axes should be quantized. And that is known as Bode's law. and it's definitely observed in our solar system. And there's not only that, we predict that the orbit of all the planets in the solar system should be tilted with respect to the equatorial plane of the sun. And that is also observed. All of them are tilted. None lie in the equatorial plane of the sun. But according to the theory of general relativity for gravity and also Newton's universal law of gravitation, all the orbits of all the planets and all the moons of all the planets should lie in the equatorial plane of the sun. And so it's a mystery why they don't. There's no explanation from those theories of gravity. Our theory shows why that is. Let me see if I'm going to be able to show that. A second here. Yeah, I'm going to show that in a few minutes. The next slide, please. This is showing you from the internet Bode's law that someone put up there nice and neat, and you can see that when we look at the period of the orbits versus the integer numbers, that there's an integer relationship between the orbits of all the planets about the sun, including Pluto, which has been declared a non-planet recently, and the asteroid belt fits on that same same graph. If we go to the next slide, that you can see from a picture how there is a very regular spacing of the orbits of the planets. They're elliptical, but not very elliptical. We go to the next slide. We see that if you do the same type of plot for the moons of a planet, particularly Uranus, Jupiter, and Saturn, which have a large number of moons, they also obey Bode's law. Now, we're going to see later on that they're not the only thing that obeys Bode's law. The whole structure of the universe does. But anyway, we'll get to that when the time comes. The next slide shows Bode's law for all the planets and the moons, and you can see the deviations. Notice that with the very simplistic assumptions that Bode made in this graph, you'll see that they're all within 5% or less of the very simplistic value. Now, Bode assumed that they went in circles. He didn't know about toroids and going on the surface of a toroid. If you put in that information, the agreement is much better than shown here. But I just wanted you to see what is commonly known. Bode's law, by the way, is the oldest known astronomical law for our solar system. So it's a very ancient law, and if you look in any astronomy book, there's no explanation for why it should hold. I mean, when we put a satellite up, we assume we can put it at any distance, and we can, but it's not in equilibrium yet. But if it were to get to equilibrium, we would find they would become quantized in a similar way. The next slide shows the origin of the planetary orbit tilt. Here I've drawn a toroidal ring and cut it in half like a donut and put the sun in the center, and I show the equatorial plane of the sun. Notice that the toroidal ring is centered on the equatorial plane, as every theory of gravity says, and that as see an example of an elementary particle below here. This is the electron. You see that the fibers of the electron, which represent the path of the planet in this case, you see that as they go around the colored toroidal ring, they also go around the cross section, and going around the total circumference of the ring one time, they go around the cross section one time. And so that I'm showing in the tilted ellipse that you see there on the upper graph shows the orbit of the Earth or a planet about the Sun, and you can see it starts at the top of the toroidal ring, and then as it goes around the toroidal ring, it also is going down the side of it. And so if we look at the orbit from the side, it looks like an ellipse. And the ellipse, though, is not in the equatorial plane of the Sun, but it is tilted by an angle theta. And those tilts are not just random. We go to the next slide. You'll see the angular tilts of the planetary orbits, and I don't know if you can see this too well, but Venus and Mercury are very close together at a one angle, and the Earth is double that angle, and Pluto is 3 times that angle. And then the other planets deviate somewhat from that. Some of the like Jupiter and Uranus and Saturn, and they exhibit what I call fine structure. So in other words, the first order effect in the angle is we see there are 3 quantized angles that the planets make with respect to the Sun, and that there's some kind of effect that splits them so they don't fall perfectly at those quantized angles, just as whenever you have quantum effects, if you have a smaller effect, it causes some deviation in the value that you see. So these angles have never been explained by any gravitational theory that I'm aware of, and in particular, the quantization nature has not been explained.
One question, Dr. Lucas. Where does
yes.
They call the line out from the Sun the ecliptic?
No, that's the Earth. That's the line from the Sun to the Earth. This is the equatorial plane. If you look in astronomy books, they don't show the data in terms of the equatorial plane of the Sun. They show the data in terms of the ecliptic.
Right.
And the ecliptic is to the Earth. Now, you see the Earth is tilted a certain number of degrees to the equatorial plane of the Sun. And so when you see the data that way, it's all skewed. It doesn't make any sense. You don't see any pattern. You have to look at it from the right point of view. And I don't know why they don't show that. I mean, I have all kinds of astronomy books and handbook of chemistry and physics, and they have a lot of data about the planets in them, but they don't normally list this data. So I've got this from an unusual book that showed you how to calculate it and put it together.
Right,
Yes?
because we're doing astronomy this year in my classes, and that's never come up either. So I see what
Yes.
you're saying. The ecliptic is really what the planets are lining up in relationship to the Earth, not the Sun's equator.
Right. And you do that because from a practical point of view, all of our observations are in terms of the ecliptic.
Right.
And I see that, but if you just think about it, it would make a lot more sense to do it in terms of the most symmetrical point of view, which is the equatorial plane of the Sun. So from a symmetry point of view, the ecliptic is not unique. I mean, it's not the thing you should be looking at. You should be looking at the point of highest symmetry. And so everything goes around the Sun, and if the Sun and all the planets had a common source, then they would all lie in the same plane, because there'd be no force to separate them or tilt them or whatever. And the fact that they're tilted at different angles, well, that's even worse. How could they possibly be tilted at different angles? Wouldn't the same disturbing force make them all similar? So anyway, there's a lot of problems there. It's just one of the unexplained mysteries of our solar system. The next slide.
Dr. Lucas, can I just ask a quick question? Is
Sure.
the deviation for Jupiter and Neptune related to their size, or or their mass, or is that some other effect? Looking at going back to the previous one, it looked like it would seem like it would tilt more if going around as if it were bigger.
I think that the moons have effect here, and we got to take those into account. The next couple of slides will show the effect of the moons. So let's go look at the next slide for Jupiter. It's the orbit of the moon Io about Jupiter. This is a NASA slide. It's not mine. Io is one of the most unusual moons in our solar system in that it is volcanic, and the dust from the eruption of volcanoes escapes from the moon and has formed a ring about the planet of Jupiter. And this ring is centered on the equatorial plane of Jupiter, where it should be. But if you can see, and it's kind of hard to see, but if you can see the dark line of the orbit of the moon, Io, it goes on the surface of this toroidal ring of the dust, and it does not lie in the equatorial plane of the planet, just as the other planets going about the sun have the same effect. But this is the only place where you can see from nature the actual toroidal ring. So I thought this was a very unusual slide, and so I show that to you. And so there we see from the NASA data. It's not my data. It's NASA data from the flyby of Jupiter or whatever. They've gotten all this data on the dust that was from the eruptions of volcanoes on the moon. The next slide shows the orbits of Jupiter's moons about the orbit of Jupiter. So the center of this, what looks like coils, is the path of Jupiter around the sun. And notice that all the moons are in spiraling orbits around it, like toroidal rings. And so when you look at Jupiter's angle that its plane makes, you got to correct for all these moons because they're contributing and they're having some effect on the angle. And also notice that these moons all obey Bode's law. The spirals are integer multiples of one another. For instance, Io is 2, Europa is 4, Ganymede is 8, Callisto is 16. And we're going to see, well, you won't see it because this is not the right talk, but if you look at DNA and proteins in the body, the big organic molecules, they have exactly the same structure you see here. And the individual atoms and molecules form spirals in those molecules that have exactly the same pattern of different relative ratios following Bode's law that you see here, but they're in the molecules. And that's because the universal force law is the same on all size scales, and so whatever structure you see in a molecule, you should see even on the scale of a galaxy, a nebula, or our solar system for a planet and its moons. So it's amazing that symmetry is everywhere. The next slide shows a side view of a ring galaxy, and you can see the spiral arm here. Can you see that arm in this picture? I want to show you that this same symmetry is occurring even at a larger scale. If we go to the next slide, this shows spiral galaxies with what are called primary charge fibers. This is a ring galaxy, and there are a number of fibers in this ring. I will show you another picture shortly where you can see there are 3 fibers in this ring, the same number of fibers that are in the elementary particle, and they're closed fibers. If we go to the next slide, this shows spiral galaxies with what are called secondary fibers, where the primary fibers split to form more fibers. Again, same notion that we see in the elementary particle model. And the next slide shows even tertiary level fibers. So this second term in the from the universal force law that we obtain when we derive the force of gravity, it's producing a lot of these effects. And I want you to see that there's evidence for these effects. They are not something that is new. I mean, something that is unphysical, that they're actually there. The next slide I like pretty good. This one shows on the right-hand side a picture of an electron or any other elementary particle that consists of 3 primary charged fibers, and on the left is Hoag's object, which is a ring galaxy. And if you look very closely, you can see it is constructed of 3 fibers, and you can actually see them going around on the surface of a toroidal ring. And that is the standard shape for a galaxy at a certain time in its lifespan, and its most stable time. So we're able to see tremendous symmetries. Now, is there any significance to these symmetries? I mean, if we now go to the next slide, from the Bible, we see a very interesting picture that's given in Ezekiel chapter 1 and chapter 10. It's often translated by the King James as a wheel within a wheel. And we have this object is being carried about or following the cherubim who are before the throne of God in heaven and leading the heavenly hosts and worshiping God as the creator. And it is natural to assume that since that's their primary function here and also in the book of Revelation, that this thing, this wheel within a wheel that goes with them, might be a symbol, a model of how God created everything. And if we have a universal force law and everything is the same on all size scales, more or less, then this might be that model. So the wheel within a wheel, the wheel is the main ring of the toroid, and the cross-section where the fibers are going around, or the planets are going around, the moon's going around a planet or whatever, is the second wheel. So we have taken the liberty to say, yeah, that might have some significance. If our universal force law is correct, and our gravitational term, our R cross V term is correct, then we would get this kind of quantization in the rings, and we would get something that might look like a wheel within a wheel. And it could be that the Scripture contains a description of the model by which all things were created by God, and that the cherubim, in leading the heavenly hosts to worshiping God, are carrying with them this model to show how God did it, which presumably when we get to heaven we'll understand better than we do now. But that's the idea. Okay, I want to go on